think it was that one. Nope, that one. Yeah. Let's go right here. Because this is not going to show up directly on the quiz or the test, I don't feel as bad moving more briskly through this. So we're just going to kind of jump around. This was the next one though when we left off. We're being asked to multiply here. What happened? Definitely cannot multiply 6. The indexes have to be the same. The indexes are not the same. I briefly mentioned yesterday that for multiplication and division, there is a way to make the indexes the same when they're not the same. Because it's not going to show up on the quiz or the test, I will not waste my time showing you how to fix the indexes. So we would just consider this to be already simplified. The cube root and you're multiplying on the square root. Can't do it. Like, you actually can. There is a way to do this. Those of you that have the math print on the calculator, like if you put this into the calculator, it will give you a result. It can be done. We're not going to be assessed on it, so I would rather I would prefer you know what to do with common indexes, such as this. Here we go. These are both cube roots. It is going to be -2. Hopefully not just because the calculator told you. It will give you the cube root of -8. If the indexes are the same, what was the rule for multiplying when it actually comes time to multiply? Outside with outside, inside with inside. What are the outside numbers here? Please don't tell me 3. 1. Yeah, these have 1s in front. These radicals have 1s in front. If you don't see a number in front, the coefficient is 1. The 3 is just an index. And 1 times 1 is 1. You don't have to do anything with it. On the inside, though, -4 times 2 is -8. And the cube root of -8, that is a perfect cube. That gives you -2. Now you wish you were here. A big part of yesterday, Hannah, was also becoming familiar with your calculator and making sure that if you have a cube root button, then you know where to find it. If you have a graphing calculator, you should. And if not, even if you don't have a cube root button, you should have a root button. And knowing the key sequences for putting in cube roots and fourth roots and fifth roots. And putting roots. Even that one, that we reviewed yesterday. First thing you should have done is multiply. 72 times 10 is 720, then there's 4 x's and there's 5 y's. Giving you enough of a head start to get that way. The reason why you are allowed to multiply, this is because they're both square roots. The indexes are the same. Okay, but now we need to simplify that radical. Best case scenario would be if 720 is a perfect square, which it is not. Maybe that has a multi-line display with print. It'll take the square root of 720 for you and it'll give it to you in the simplest radical form. But if not, you have to do a tree. Do a tree with 720, hash brown, bring out pairs. What's coming out? What's coming out? I think you're saying the right, but I hear it. 12 would be good. 2 times 2 times 3 is 12. How many x's can come out? 2. How many y's can come out? 2. What's staying on the inside? 3. 5 and y. Not that you so you know what's good news or bad news, but you won't have to worry about absolute values because we will not be simplifying radical expressions. We're only going to be solving in the absolute values that when you're solving. But if you were to be doing this on the assessment, would any of these variables carry absolute values? Neither of them would, but for multiple reasons. First of all, even if they needed an absolute value, they both have a square. Squares make numbers positive. So the square would be the absolute value even if you needed it. And because somewhere on the screen there are instances of those variables having odd exponents. All right, so let's jump around now. Let's go to some division. The main focus of today was adding and subtracting, but I just want to go. When we divide, I give you a list of steps. I told you that either of the first 2 steps are fine to start. But once you pick a starting point and just work your way down the list. I purposely put division first though, because you can't always divide, but if you can't divide, I tend to lean that way, that I would prefer to divide first. Can this be divided? Partially, yeah, sure. Yeah, they're both square roots and on the inside. I can't divide 20 and 45 entirely, but what can I divide them by? By 5, so this becomes a 4. That becomes a 9. With variables, when it comes to dividing common variables, as we worked on operators of exponents before, we subtract, and the shortcut I showed you was the big minus small, and leave it where the bigger one is. Because these are inside of a square root, they would still be inside of the square root. On the top I have a 4, on the bottom I have the 9. For the a's, 2 minus 1 is 1, but the bigger one's on the bottom, so I'll leave the a on the bottom. For the b's, 3 minus 1 is 2, but the bigger one's on the bottom. So you're going to see that 4, you're going to see that 9, you're going to be really tempted to simplify. You're like, oh, look, I know those. And that's fine if you want to do it like it wouldn't be wrong. You can still get the right answer if you were to take the square root of 4 and the square root of 9 next. But just for the purposes of uniformity, since I started off with division, if you look at the steps I gave you yesterday, what should you be looking to do next? And I like to rationalize next. Rationalize means to get rid of the radical in the denominator. Keep this in mind, because we're going to do this again later, but in a different form. Who remembers from yesterday how we rationalized? Really, what we're multiplying by is 1. Like the one book that we're going to put away. We're multiplying by 1, but how do we write the 1? What is that thing we're going to write? The denominator over the denominator. So square root of 9ab squared over square root of 9ab. Anything divided by itself is 1. Times 1 is itself, so I'm not changing the value of the red. When I multiply the red by the blue there, it's not changing what the red is worth. In reality, you're multiplying by 1. But you're going to change the appearance. The main thing being that now in the denominator, anytime you multiply a square root times itself, in the numerator, since they're both inside of a square root, I can multiply them, and that still works out pretty well because I get 36 squared. And then finally, we continue down the list. The next step would be to simplify. When we talk about simplifying, we're talking about the radicals. And if you rationalize correctly, there should be no more radicals in the denominator. The only possible radical should be in the numerator. What can I bring out of that radical? A 6 would be the obvious because of 36. And what else? And a b. Good. Yeah, we're done. You should never have to rationalize twice. But when you start off with division, you may have to divide twice. Even though we were able to divide at the beginning, there is more division to be done here at the end. Because now instead of inside the radical, we're looking outside the radical. I can't divide 6 by 9 entirely, but I can reduce it. By which factor can they be reduced? 3. This becomes a 2, this becomes a 3. I can't do anything with the a, but for the b's, 2 minus 1 is 1, and I put it where the bigger one is. So on the top, all I have left is 2 and the square root of a. On the bottom, I have a 3, a, and then b's from the subtraction. Everyone stop picking on here. What I think you guys were doing yesterday, where you were like chasing each other around the court. You weren't able to catch that group? Not even the teammates. Any questions, Rick? Alright, let's move on to adding and subtracting. Rules for adding and subtracting radicals. Question for me, Hannah? Sure. Not sure about the Lexi you want to ask. Still have to have the same index. Just like with multiplying and dividing. The difference would be though that if the indexes are not the same, there's no way to make a match. Even though I didn't show you how to make the indexes match multiplication and division, there does exist a way with multiplication and division, not so with adding and subtracting. And you're going to see, in many ways, radicals behave like variables. The rules for radicals are similar, in some cases the same as with variables. So how do we add and subtract variables? What rules govern the way that we add and subtract variables? If I asked you, hey, what's 2x plus 3x, what would you tell me? Huh? Yeah, 2x plus 3x would be 5x, right? But then if I say, oh, hey, what's 2x plus 3x squared? We're thinking about it that long? We can't add them. Why not? They're not like terms. Thank you. If I said 2x plus 3y, can I add them? No, because they're not like terms. Well, a lot of the same things are going to apply to radicals. If you do not have the same index, you can't add them. Now here we're going to add something new. If you do not have the same radicand, we learned what that is yesterday. What's a radicand? The stuff on the inside. Yeah, that's going to match up too. So it's almost like in order to add or subtract, they have to be like terms. Or in this case, like radicals. The radicals have to be identical. Now, even though we can't fix the index, okay, it is possible. It may or may not work, and it's going to vary. But if the radicand is not the same, you might be able to make them the same by simplifying. If you simplify them, they might become the same. Not always, but sometimes. Then another main difference, but you're going to see some parallels with variables. Like when I originally asked you here, hey, what's 2x plus 3x? What did you tell me? You told me 5x, right? 2x plus 3x is 5x. What happened to the x's? It's the same. I had an X, I had an X, and at the end I have an X. Nothing happened. So where did the addition take place? In front, in the coefficients. Same thing with radicals. We're not going to touch what's inside the radical when it comes time to add. We're only going to add it from the outside, the coefficients. So here we go. Let's start off prime example. Here we're very nice. We have the same index with the both square roots. The radicals are the same. So what is 9 square root of 5 plus 8 square root of 5? Oh, easy. Square root of 5 stay the same. 9 and 8 is 17. On the next one, there's 3 terms. But look at all the radicals. They're all square roots. The indexes are the same. They're all the same radical. So we can just combine the numbers on the outside. What is 8 minus 6 plus 5? It is 7. The square root of 2 stays the same. Now, one thing you may have to do sometimes when you add or subtract, as I briefly mentioned, is that you may have to eventually simplify the radical. But why can't those radicals be simplified? Not only are they not perfect, they're prime. That's the word. This next one just shows you that we can do it with variables, not a big deal. Here, how about this one here? Do that one. Oh, Romero, look, they're both square roots, but you said that the radicals have to be the same. They're not the same, so it must be that it's already simplified, right? It's not like, what can we try to do? Let's try to see if maybe simplifying would help. Since we all know how to do factor trees now, I can just tell you that this is 5 square root of 2. I can tell you that this next one is 3 square root of 2. Look at that. Before they didn't look the same, and now they do. Steph is impressed. Very impressed. Very good. And now this becomes 8 square root of 2. Look at the next one. Hannah Montana, since you weren't here yesterday, I think I saw you a little bit surprised by what we did with a negative instead of a radical before. But if we have an even index, what would happen if you have a negative number underneath an even index? It doesn't exist. It'd be imaginary. It doesn't exist in the real domain. It doesn't fall in the number line. But odd indexes are fair game. If you have a negative under an odd, you can just bring it out. The reason for that is the cube root of negative 16 is the same thing as saying the cube root of negative 1 times the cube root of 16. And the key being, what's the cube root of negative 1? It's just negative 1, yes. Negative 1 times negative 1 times negative 1. Negative 1. So I'm going to bring the negative out. You might need to do a tree. For the other ones, I'll just do it in my head. But this becomes, I believe, 2 square root of 2. So I have the negative that I brought out. I can bring out another 2. And I leave a 2 on the inside. That should be a cube root. Then plus on the 54. Now, oh look, if you were to do a tree, here, let's just do a tree with the biggest one here. Let's do the 128. This one. Would you agree that's a factor tree of 128, the prime factorization? It has 7 2s as prime factors. If you were to do a tree when these are cube roots, in order to break out of the radical, what roots do they have to get in? Yeah, the triple, whatever the index says. So here I could bring out 2 2s. That'll be the last one at the end. And on the inside stays the 2s. For the 54, I want to say a 3 comes out, it would be 3 cube root over 2. And then the last one just said minus, if 2 come out, it will be 4 cube root over 2. I couldn't add and subtract before, but I can do so now. What is negative 2 plus 3 minus 4? They're all cube root of 2 now, they can be combined. It is negative 3. So this will give me negative 3 cube root of 2. How about this one? Can't simplify any of those. 7 and 11 are fine. And I combine any of them. Which ones could be combined for this? They can't all be combined. Negative 8. The fourth roots with the fourth roots. Square roots with the square roots. What is 5 plus 1? 6. So then people bring it to 1 here. So 6 square root of 7. Negative 8 plus 10 is plus 2, 4 root of 11. How about this one? Don't overthink it. Confident. Paying attention to what you're doing. Your eyes closed. That looks complicated. You can manage. Something. We have just gone over the rules for radicals. Kendall, you got an idea? You're right, you can't do anything to it. And why can't we do anything to it? Well, I'm going to write it in specific form, but that's some explanation. That's what she said. I want to know why. Close enough. Yes. The radicals don't match. I cannot add square root of 7s with square root of 5s. The fact that they're both square roots works out well. I don't even need to worry about the fact that there's x's there. It's just the radicals don't match, and there's no way to fix them because 7 and 5 are both prime. So this would already be a simple form. To simplify means to do operations. The operation we're being asked to do there is addition, and those two can't be added. On your thinking. Question? Okay, so you can do that one. You got it, Alexi? Yeah. Calculator. So, as it, so, hey, Mr. Miller, you just told me that if the radicals don't match, that we can't add them, we can't combine them. So, bam, simplify. Easy peasy, lemon squeezy. Well, no, unlike this last one, some of these numbers, you can simplify the radicals. Maybe it means nothing. Maybe it makes no difference. Who knows? Maybe this is, maybe you can't add and subtract these, but you won't know until we simplify. Uh, since we know how to do trees already, I'll do it in my head. This becomes, I believe, 2 square root of 3. Alexa, correct me if I'm wrong. This becomes 5 square root of 3, and this is drops as if it was hot. And then again, a very easy thing to carelessly overlook is that there's a 1 in front here. So 2 plus 5 minus 1, use your fingers. And okay. Now we're going to start bringing pieces of all of these together. All the operations. How do we normally multiply binomials? Binomials. This, yeah. These can't be added. These can't be added. But if I want to remove the parentheses, I would FOIL. FOILing is a type of multiplication. We did multiplication yesterday. The rules for multiplication were outside numbers with outside numbers and inside numbers with inside numbers. So here we go. 4 times 5, those have nothing to do with a radical. So fantastic, that gives me 20. How about this next one? What's 4 times 4 square root of 2? Cheesy for cheesy, yeah, it is multiply the outside number to square root of 16. On the next one, 2 square root of 2 times 5. The last one's going to be the most interesting one.
Yes, sir. Multiplying square root of 2 by square root of 2, so remove the radical and.
Wow, that's actually very good. See, if you have the most basic understanding of this, and this is like what the kids did last, don't write this, don't write this, don't write this, don't write this. It's not that it's wrong, but by the most fundamental understanding of the rules, if you say simply inside with inside, outside with outside, when you do this last one here, when you do this you would say, well, that's 8 square root of 4.
And 4, you could.
Well, that's the thing. What's the square root of 4? 2. Or you could just know when you, like what you said, which is when you multiply a square root times itself, the square root goes up, you just get the 2. What's 8 times 2? If you want to write the extra step in, write it in, because if not, you're going to be later like, wait, I don't get it. How do you get 16? That's what 2 square root is. But wait, there's more. Now that I remove the parentheses, I have 4 terms here. I need to combine them that are like. Can any of these be combined?
Yes.
Which ones?
20 and 16.
Yeah, 20 and 16, those are both rationals. 20 and 16 is 36. And then 16 and 10 is 26. Let me just keep this. Please don't add 26. Can't be added. Wait, but those are both outside numbers. Yeah, but we're adding the radicals have to match. You can't add a rational with an error. But those are like the questions they love to put on standardized tests. Whether they're like, what happens if you add a rational with an irrational? What happens if you multiply, an irrational with an irrational? Like, when it comes to adding, you can't add a rational with an irrational. Question? Okay, let's want to try that one out for size. See if you can do that. extra line. Minus 2 square root of 7. Let's see how she got that. 3 times 5, 15. 3 times square root of 7 plus 3 square root of 7. Negative 7 times 5 is minus 5 square root of 7. These don't say away, but they're not right. Yeah, so I'm not just multiply them. On the outside, like for instance here, 3 times the 1 on the outside gives me 3. And this doesn't have a square root, so it's basically tossed. If I were to ask you what's 3 times x, you would tell me 3x. And we said variables behave like radicals. So 3 times square root of 7 is just 3 square root of 7. How about at the end? What is negative square root of 7 times positive square root of 7?
Negative 7.
Just minus 7. The square root goes up. Wait, but I got square root of 49. Okay, cool. That's fine. There's nothing wrong with that, but what's the square root of 49? 7. Yeah, make sure you have a negative. Positive times negative is negative. 15 minus 7 is 8. Okay. Still have a binomial, but now I'm squaring it. We worked on this in the first semester. Sadly, what do people are so predisposed to wanting to get this exponent and distributing it. Au contraire, mon frère. What would be the most basic thing you could do? What's the most basic formula that you can do here? Sure. Write it twice, or change the multiplication. Get the square, change the multiplication, so you get 4. A little bit more advanced is to do a binomial expansion through Pascal's triangle. That's a little bit more, it's more friendly when it comes to mental math. But if you don't feel comfortable with it, like if that was like a 7th power, yeah, I would only use Pascal. Even if it was like a 3rd power, I'd probably use Pascal. But for a 2nd power, I would just tell you to do that times itself. And now we FOIL. What's 2 square root of 5 times 2 square root of 5? What? 2 times 2 is 4. Square root of 5 times square root of 5 is 5. 4 times 5 is 20. 2 times 3 is plus 6. 5 and 2 is 10. Plus 6, 10. What is 3 square root of 2? For Lauren. What's 3 square root of 2 times 3 square root of 2? 3 square root of 2 times 3 square root of 2. Thank you, sir. 18. 3 times 3 is 9. Square root of 2 times itself is 2. 9 times 2 is 18. 38 plus. There is a slight chance, it didn't happen here, but there is a slight chance that maybe that radical could have to be simplified. But even though 10 is not prime, on 10 all I have is 2 times 5. I can't bring anything out. It will just stay like that. I hate to say it, but sadly another mistake that people make is combine those. That would be the same thing as like telling me that 38 plus 12x is 50x. That amounts to the same. Questions? Ooh. What operation are we being asked to do here? What operation are we doing here in Rounders? Yeah, I mean, you could say subtraction, but you can't subtract those. But we have division. They're all square roots, right? So, and we divided before. How is this, the one that we're doing now, how is that different than the one that we have up here on the screen? This is the key, this is like the key thing to understand how to do this. Understanding how it's different.
Can we take them into two fractions where it's like d over 2, d radical 2 over negative radical 2?
No, if it was the other way around, if this was on top and then like and the other was on the bottom, then you could distribute it, but you can't distribute it that way now. Or it doesn't work. It's not. The closest one has been Alexi. Not he didn't say it right. He pointed out that there's two radicals in the denominator. But the issue is not that there's two radicals. If there's one radical, you gotta get rid of it. It's not the fact that there's two radicals. The fact that there's two terms. The binomial. Traditionally, yes, I would say these are probably missed the most. Students tend to get these more incorrect than they do these, like we did before, where there's only one term in the denominator. But if there is like a silver lining, these should actually be more familiar to you. If you have two terms in the denominator, you have to rationalize first. So I gave you the steps. Forget about dividing. Whoever says they can't be divided, yes. As it is right now, yes, you're correct. They cannot be divided. But they can be rationalized. And the way you would rationalize should actually be more familiar to you. What else this year have we rationalized, or I guess last year, with complex numbers with imaginary numbers. By format, imaginary numbers, right, the complex numbers, those were also binomials. Those are two terms. Who remembers how we rationalized complex numbers? I can't get very good. Complex conjugates. Well, this is not a complex number. So we talk about complex. How would you rationalize this? Multiply by the conjugate. You should know what it is. What's the conjugate of square root of 5 minus square root of 2? Square root of 5 plus square root of 2. And just like before, we multiply on the top and on the bottom. Because we're really just multiplying on the bottom. In the numerator, multiply, which in this case is going to involve distribution. 3 times square root of 3 square root of 2 times square root of 5 is 3 square root of 10. What's 3 square root of 2 times square root of 2? Very good. This is actually surprising to somebody got this first period. So what we're doing here is multiplying conjugates. Even though the fact that they're not complex, who cares? The fact is that these are conjugates. And we have these forces here every time that we multiply conjugates. What is the result? Those complex conjugates of the sum of squares.
This is just like the A minus B squared.
Difference of squares, very good. Anytime you multiply conjugates, you get a difference of squares. Now I'm actually faster than the other class. Fire today. Difference means subtract. Squares is the key thing. This allows you to square the square roots. And what happens when you square the square root? No mas. I'm going to go ahead. This isn't as strict as with complex numbers that you have to, like, remember with complex, you have to write the real and then the imaginary. This isn't as strict, but typically when you have a rational and an irrational, you write the rational first. So I just switch the 6 to the front. This becomes now just 5 minus 2. Yeah! Finito. A lot of times you will be done here. You don't have to do anything else. But if all the outside numbers have a common factor, if the rational, the irrational coefficient, and the denominator have a common factor and needs to be reduced, this can be more than this. This can actually be divided. This is kind of what you were talking about at the beginning, Julian. When I have two terms on the top and one on the bottom, yeah, then if I can divide, I can go ahead. So we get 2 plus. You can do this one. But wait, Mr. Romero, this only has one radical in the denominator. The key is not the number of radicals, it's the number of terms. And I have 2. Step, ready, set, go. Start, go. Like a relay race. I got you. Go, go, go. What is the conjugate of 3 plus square root of 5? So I go 3 minus square root of 5. 3 minus square root of 5. 6 square root of 7 minus 2 square root of 35. 3 squared minus. On the top, can anything be simplified? Nope. On the bottom, though, we get 9 minus 5, which gives me, oh, am I done? Why not? I should have reduced. Yeah, we have common factors we can reduce. 6, 2, and 4 can all be divided by 2. So this becomes 3 or 1 and a 2. So we get 3 square root of 7 minus square root of 35. Maybe we do 1 or 2 more. Let's go for the. Do that one there. Which binomial am I taking the conjugate of? Denominator. What's the conjugate of 2 minus square root of 3? 2 plus square root of 3. In the numerator, we're going to FOIL. So we get 8 plus 4 square root of 3 plus 2 square root of 3. And then square root of 3 times itself is just a regular 3. What do we get in the denominator? Somebody not named Alexi. Tell me. Difference of squares. Difference means minus. 2 times 2 is 4. Square root of 3 times square root of 3 is just 3. And what's 4 minus 3? 1. So actually the denominator is going to just cancel out. We're not going to even need the denominator anymore. There's a 1 on the bottom. And then once we combine like terms like I do in the hood, we get 11 plus 6. Any questions for me? Tomorrow, where are you going? The lab. We'll start off working on that pre-test. I assume everything that was always. I'm assuming you're going to finish pretty early, so I will evaluate if and when you finish to work on the homework. And then back here, working on the bring your document back here on Thursday.